recording in progress now is the lecture recording. So let me close this. See no stress, we can keep that open. Empty pages are welcome. And so we're talking about this membrane model, and the last slides that lead to the ultimate understanding, of why the resistors are placed where they are. And so I last time I explained this relatively complicated approximation of the membrane mechanics, which was extracted from many experiments, many finite element simulations, as a matter of fact, and with some parameters that can easily be obtained and others that are really only numerical parameters. So that's a phenomenological model. And as I said, it describes the pressure needed to obtain a certain deflection, a center deflection of a square membrane, in terms of this polynomial model, which can be graphically represented like this. So pressure, now the ordinate is horizontal and the abscissa is vertical, and it occurs, the response consists of a linear term and then a cubic term deviating from the linear term. And of course, the same graphic can also be read the other way, as W as a function of P, which is a complicated function because it's actually a root of a cubic equation. But I mean, graphically it's there and it's computable. And so now we need to we would like to have a measure of the sensitivity, not just by assumed numbers, apply 1 bar and then assume that the stresses are 1.4 megapascal and 20 megapascal as in the last exercise, but what is the stress really, for a certain thickness of the membrane and so on. And so what I propose here, and actually what I propose here is just an assumption, or based on an assumption that actually the membrane is operated in the linear region. So we are, whatever the dimensions are, we are only operating it in this linear region, which is certainly true for thick enough membranes, or membranes that are not too large enough in comparison with their thickness. So it has to do with their aspect ratio somehow. And I have to go back to this equation. So the terms that we consider is this P and this prefactor multiplied by A up to here. And we neglect that cubic term. And I actually, before the lecture, I tried to rederive the equation on that page, 2 pages later, by inserting, of course, this A, whatever is here, into this equation. Let's see what we have here. So this equation, under this additional assumption that there is no pre-stress in the membrane. So sigma 0 is 0, which also means that epsilon is 0. And so that this term is gone, and we have this epsilon 1 critical. I don't know why I wrote 1 here. Let's replace that by 0. It makes much more sense because it's about a pre-strain, and here as well. And I looked this up and I couldn't actually, it's pretty simple to now calculate W as a function of P, by just shoving over some of the coefficients. And I didn't end up at this result here, which is written here. Actually, this thing, actually should be this numerical factor of 4.363 in my current opinion, because this is the only thing that remains here of this term, this guy here, minus with an additional minus, so it makes 4.363 divided by 1 plus nu, but this is multiplied by 1 plus nu, so 1 plus nu is gone. So it's essentially, A is essentially C1 times 4.363. So that's here. And if we go back here, we find this A down here as C times 1.363. So please write that correction here. So now we only have W0, which is the center deflection of the membrane. So how does the membrane deflect somewhere else? And it turns out that a relatively good model is given here. So this is a function that depends on x and y. And it has a term that only depends on x. And another term, well, let's put f of x, another term that depends only on y, the same function. And this function, what does it look like? So we have here the center, we have here a half, and we have a half, so that the membrane size is a, and this is basically the clamping, and now what does how does this function behave? It's a function that is the square of well, and it's actually even wrong, because let's face it, it's this f of x. What does it look like? It looks like a parabola that goes to 0 at the edges. Goes to 0 at the edges. Because at x equals a half, this is equal to 1, and so 1 minus 1, okay, is 0. And in the center, this function is 1. And now what is amiss here is that each of these functions needs to be squared. By this way, this function becomes, or let me draw that by another color, this squared function does what a clamped edge needs to do, namely to be horizontal at the edge, to bulge up and to bulge down again, and to become horizontal again as the membrane tangentially goes into the wafer at this level. So this is also to be added here. And with this function, if you now calculate the curvature at this location, so for instance, dw, twice the derivative with respect to x, it's always called x prime because of this 45-degree rotation, you get the curvature here. And now the membrane is this curved piece of material with a curvature given by the second derivative. And of course, there is this neutral plane that experiences no epsilon xx, or x prime. However, on the surface, of course, there is a compression under this positive curvature. And that compression is given by the second derivative multiplied by h half. H half is half the thickness of the membrane. There's another half below the neutral plane. And that is easily seen. You can, well, use a geometric argument with a circle going around and then see how much this smaller circle with radius shrunk by h half has a smaller length, and that relative smaller length, or that relative length change with respect to the length of the neutral plane circle is epsilon xx. That's easy to see. And the same applies for epsilon yy. And you can also apply some or calculate some shear stresses by doing these mixed derivatives of the deflection function, this 2D deflection function. And then the stress on the membrane surface can easily be calculated by an isotropic model, actually. And that is then given by these formulas here. So that's for the biaxial stress load, where epsilon xx, or where the properties are actually isotropic. And so this is not a full anisotropic mechanical model again. And so you have these stresses as a function of whatever the strains on the surface of the membrane are. And they can be represented And then they can be turned into resistance changes for a resistor located at a particular location of that distribution. So let us maybe look at the strains first. So here is a strain at the membrane surface in this assumption of linear response for the model that for this deflection model that I just wrote, which is a reasonable model. I mean, it matches the real deformation of these reasonably thick membranes fairly well. So what do we see? Epsilon XX, this is the X. Now I dropped the primes here. We have the one edge defined as the X-axis, the other membrane edge defined as the Y-axis, and epsilon XX is the stretching in this X direction, and obviously along these lateral boundaries, epsilon XX must be 0. That's clear. However, along the other boundaries, because of the curvature, of course there is an epsilon, and it's negative because there is a compression at the edges, and in the middle of the membrane, where the membrane bulges down in a convex way, convex, yes, it bulges towards you, convex way. Of course, there is a tensile strain, which is indicated by this positive value. And the epsilon YY is rotated by 90 degrees, no surprise. And an epsilon XX can also be calculated. And you see that actually there is shear stress somewhere in the middle of these quadrants of the membrane. So if you wanted to apply a shear stress sensor, which you could place it somewhere here in these alternative locations. And you know how a shear stress sensor might work. I mean, a shear stress sensor is also a Wheatstone bridge under appropriate rotation, and then you could then calculate the sensitivity, and you would for sure find that actually it's unfavorable. These shear stresses are smaller, and the piezoresistive coefficient you can apply, with the sensor elements are not so favorable, and so you can drop the shear option. So now we have epsilon, and we need sigma, of course, because sigma is the object that we need to translate the mechanical deformation into some resistance changes. So what are the sigmas related to these epsilons? And that's shown on the next slide. So here you see sigma as a function of x and y, and we see that there is a normal stress component along this membrane edge, which is very positive here in the center. It's quite negative here in the middle of these edges, perpendicular to the x direction. And so by just looking at this, one would naturally put a resistor here or here at these locations, at the extrema of the stress distribution. And sigma YY is, well, the same function as sigma XX, just rotated by 90 degrees. So certainly there is reason for putting resistors here or at the back or maybe at the top. At the top is maybe not such a good idea, because if the X resistor and the Y resistors are on top, then again they experience the same stress because of symmetry reasons. So likely that's not a good idea, and therefore that is the reason why one puts resistors at these locations. So the resistors are placed in the middle of these membrane edges, because there one of the stresses is quite large, and the other stress that comes in the difference doesn't play such a big role, and the pi coefficients match quite well. So if we go back to these resistance changes, we have the sigma XX times pi 1,1, always prime now again, sigma YY times pi 1,2, and then for the other kind of resistor, well, sigma YY, pi 1,1, and so on. And so if I take these values that one computes here, or sees here computed on this slide, if you take that and implement it, you obtain a sensitivity that follows the following rule. So the delta V per V in per pressure is equal to some numerical factor times the pi 4, just like Jonathan also found before as a proportionality factor, and then well, some material and some geometry value. And the interesting part of that formula is that, you see, the absolute dimensions don't play necessarily a role. It's their ratio. It's the aspect ratio of the sensor that makes the sensor sensitive. So having a large membrane per thickness will make the sensor more sensitive. But then you have to remember that this formula was obtained under the assumption of a linear response. And if the membrane is too large, it's not going to be linear for very large pressures. So this sensitivity only applies for sufficiently small pressures where the membrane remains in the linear regime. But for a small response model, it shows that only A over H play a role. And that's interesting to see because you don't necessarily know that from scratch, because you say, oh, this must be a complicated function of A and H, some weird connection, but it's a very simple connection. So if you would like to have a larger pressure range, I'm sure that making the membrane smaller and smaller will let you reach that larger pressure range, because the membrane has better chance to remain in this linear regime than if you have a very large pressure range. But that has to be confirmed based on this function here, where the linearity and the non-linearity actually can be evaluated. So here you can plug in dimensions and then see whether the second term, the nonlinear term, is actually negligible in comparison with the linear term. So what I just said certainly needs a more critical consideration than I just said. So in conclusion, E plays no role. That's also interesting. Why does E play no role in this formula? Because E enters in one way by letting the membrane be deformed. The smaller E, the stronger the deflection of the membrane is. But the deflection multiplied by E makes the stress, and the stress makes the resistance change. So the E cancels in this process. Absolute pi and pi 4 should be as high as possible for maximum sensitivity. So this tells you that this P resistor value is certainly P resistor use is certainly best, and that matches also the orientation of the membrane thanks to KOH etching. So everything concurs to an optimal sensor. Yeah, I think that was it here. Yeah, and yeah, with that I conclude this chapter on piezoresistors and mechanical sensors of all types, and I will continue next week with the thermal sensors. And actually, in order not to overload myself with weight, I'll give it to you. I have 6 pieces of script here for you to take and then bring back next week. And with that, I stop here.